Good morning, everyone. We are Group 4 from ME444, and today we're going to present on our idea of a hydraulic excavator. Oh, I'm Kendall Snyder.
I'm Owen Bailey.
I'm Sabrina Alhaj.
I'm Akash Khanwani. So the idea was to create an interesting toy for kids ages 6 and up to not just play with but learn from as well, and hopefully go into engineering careers in the future. So we decided that the excavator did a pretty good job at that with its multiple mechanisms, the hydraulics and stuff like that, motors. So before we designed it, we wanted to put it down on paper, the concept itself. And as you can see, we have tracks, like tank light tracks that would move the excavator forwards and backwards. And then we have the base plate that rotates so that instead of turning the whole machine, just the plate can turn so that the arm can scoop stuff around itself.
And then here's our CAD model of our design of the excavator. And now we're going to go further into the design of the parts. So first we designed the base chassis for the excavator, and that includes 4 plates, and they all fit together with notches and extrusions. And in these side plates we have 5 holes, 4 for the dowel rods that run the track on it, and 1 for the motor to connect to the track and run it. And then on the top plate we left it removable so it can lift up and the electrons can be easily accessible. And it also has a cutout for the servo motor to rotate the rotating plate, and then a connection for wires to run through for the motors on top. And then next, one of the most important parts of our excavator is the rotating plate on top here, because it encases like all of the main components of our excavator, including the arm and the syringes to drive the arm. So in designing this, we have a spot for the servo to connect to and rotate. We mounted bearings onto it, and we designed little holdings for the syringes to stay onto the base so that in motion they wouldn't fall off. And then we also designed a rack and pinion system to drive the syringes to move the arm, which we later found out didn't have enough torque to move, and we would in further iterations use more like a worm gear like mechanism. Going into the arms of our excavator, the arm of our excavator, it includes 2 main arms and a bucket, and each is driven by a hydraulic syringe. And this is connected to this 3D printed base piece that's connected to the base, or the rotating plate on the base. And when the syringe moves, it moves the arms. And the arms were designed to be laser cut out of acrylic, and we put 2 on, 1 on each side so that it had good support, because all the forces will be running perpendicular to the acrylic. And next, Sabrina's going to go into the CAD design, or the assembly design.
So for our Creo design, we, as our demo will show, we had the 3 motors, each on the rack and pinion bases, as you can see here. And as you can see, they'll drag and pull, and like as the syringe would go in, of course it has like a certain aspect that it can go through due to the plunger size, but the gear would rotate, allowing the syringe to push forward and back, and as Owen stated, this would control the arm motion. Going along with that, as you can see, we have a lot of moving components here. So the base also rotates, and that will be shown in the demonstration that we have our rotating base from our servo motor. And then the last part that we had rotating was the motors that here, and it's kind of hard because there's no track on this one, just because it's kind of hard to model in Creo, but the motors would rotate here as well. And so as you can see, like with the whole assembly, the arm would kind of rotate with the syringes, allowing the syringes to open and shut as the arm goes up and down. Kendall is going to go into our manufacturing.
So after we had all of our CAD modeling done and we figured out all of our dimensions and tolerancing, we went into doing our actual manufacturing. And we had two main methods that we were going to use to manufacture parts: laser cutting and then SLA 3D printing. And depending on the purpose of the part, how strong it needed to be, how complex the design was, that's how we chose which method to use. So for all of our panels and gears and the arm components, we used the laser cutting because they were kind of a simple shape. And we also needed them to be really strong to support the rest of the mechanism. And then for some of the more complex pieces, like all of our rack and pinions, and then all of the connectors that we use to connect the syringes to the base and to the arm, and obviously to the rack and pinion, those were too complex to try and laser cut, so we had to 3D print them, as well as the scoop, obviously. And then when it came down to doing the actual assembly, after we had all of our pieces, the first thing that we made was the chassis. So as you can see, like Owen talked about, we have 4 panels that are open on the back and the front, and then that top panel comes off, and that was designed that way so that we could house all of our components, all of our electronics in there. And then we have 4 dowels that are going through that have bearings on the ends for our tracks to run on. And then we went and assembled the rotating plate, which has our 3 rack and pinion mechanisms, and then those are connected to our 3 base syringes that have their 3D printed components to the plate. And then by far the most complex assembly was the arm that has its connection on the bottom, which we 3D printed to the rotating plate, and then all of the arm panels, and they were designed so that they would be the perfect width apart to have our syringes fit on the center. And then that was all using 5mm nuts and bolts. And then we had to connect all of our tubing to the ends, which is complicated every time we try and fill them up. But the tubes then connect all 3 of the arm syringes to a base syringe, so that when the base syringe is pushed forward, that extends the connecting arm syringe, which causes the arm to move either up or down. So then for all of our electronics, we have 2 DC motors and 1 servo motor. The DC motors are what powers our tracks, and the servo motor is what rotates our base. We were planning on having 3 additional motors, like Owen mentioned, that would electronically power the arm, but because it seems to be a common theme, we did not get strong enough motors, and so it's quite a heavy arm, so we ended up having to push those by hand, but in the future those would be installed as well. And then we just used our ESP microcontroller and an H-bridge and connected that all to a 9-volt battery to power everything. So for who this toy is targeted at, we're looking at children ages 6 and up, but obviously it's a little bit complex, and so we're hoping that it'll involve their parents and kind of be a fun experience for both groups. The idea is to target tinkerers who like to build their own stuff and hopefully have an interest in mechanics and electronics and eventually engineering.
So now for like what makes this toy unique, the way it will be packaged and like shipped out for assembly would be that the parts are all separated. So then once the child would get the toy, he'd be able to put it together himself, and then like he or she could like work together with the parent, of course. But this isn't like a Lego toy that takes you like 5 minutes and then sits in like the closet for like the rest of the time. This would be something that they take care and effort with. They'll learn about the gears, they'll learn about hydraulics, they'll understand like the toy a lot, and therefore it's like kind of bringing kids into STEM at an early age, and also like allowing parents to bond with their children. And then for the play value of the toy. So for this toy, it's a lot, learning experience from this toy allows a child to say, look, I put together my own robot. Or guess who now knows how to use hydraulics? Because that's what every kid wants to say. And for the customizability factor, all the colors in the tubes. So for our group, we like the colors red, green, and blue. But maybe a boy doesn't like blue, so he chooses orange. He can put orange instead for the color. So it allows that customizability factor. And then also the acrylic allows you to see like all the hydraulic process and all like the electronics really easily. And then of course you can pick up sand or candy in our case, because that's more fun. And then for opportunities for improvement, of course, kind of as Kendall and Owen stated, we would want stronger motors just so this could all run electronically. And then we'd also want larger syringes, which as you'll see with like our base arm, the syringe right now cannot hold it up due to its smaller size. And then we would prefer to have more linked tracks rather than Velcro.
moving forward, we'd like to design this keeping our consumers in mind now. Come up with a good assembly sequence so that kids can put it together easily. Box the screws in a way where kids can learn about imperial and metric screws as well as they put the parts together. And like she said, the motors and whatnot will also be figured out. Make the electronics a little more neater, so that kids can work with it. Yeah.
Now we'll have a demo.
Just for
Use your design however you want it.
You come over here, you want to go on this side?
That works.
You wanna try that?
Yeah, so first we're going to show you the movement of the tracks.
And then
So then this would be powered with a motor, but he's just going to do it manually. Open this guy up a little more.
Yeah, I'm trying. I think we got air too.
I don't know. So then it picks up sand or nerds.
Want to rotate it?
And then, yeah, sure.
A bit of a jump when you start.
We can do that. And if you guys want to drop it back.
There you go. Anybody have any questions?
The first one is like how you solve the problem of the tilting. Yesterday was falling.
Yeah, you were there for that.
What was happening there?
So yeah, so basically this is really top heavy. And luckily the base is pretty heavy too, so we weren't having an issue of it tipping on the base. It was just this plate because it's elevated and held in not many spots. So we thought that adding these rolling bearings would be enough, but as soon as you started to turn the arm, it would tip. So what was actually happening is that the servo is connected and then it's just feeding through that hole in our base. So by securing the servo to the base, that's what was lifting up. So all we did was secure the servo to this bottom base, and then that was enough to secure it all.
And we also inserted a screw from the top plate into the servo so everything's held together tightly.
The second one will be how would you do to make the band be like tighter so you can transfer all the power to make it move?
Okay, for future like design, we would plan not to use the Velcro. That we found this was kind of just like an easy solution because we were at our like the lengths of our budget and we didn't really have any more money. So we decided to use the Velcro because it was something that would run and actually move the excavator in like a cheap and quick way. Yeah.
But we would use something with more tension.
Yeah, and it's kind of like we were looking for like more of a rubber strip, but that would be difficult to like attach to itself and adjust the tightness. So we decided to go with the Velcro that can attach to itself.
I think we go with metal links in the future, with that we can adjust lengths with as well. With Velcro, it was easy to adjust the length of the track as well, so that's why we went with it.
The liquid in the tubes, is it water or something else?
It's water.
Yeah.
Just has food coloring.
Was there like an extra kind of fluids analysis you had to do by using the hydraulics, or was it just kind of like pretty intuitive without it?
We kind of just assume because we just assume water is an incompressible fluid, so how much this syringe moves, this syringe will move by the same displacement.
Less fluid analysis, more trial and error, for
Yeah.
sure, on our end.
Quick question. Is there any other hydraulic toys you have found in the market?
I'm not too sure if there are any ones that you can like readily purchase.
I'm sure that they exist, but not
And-
many that I've seen.
And plus, like what I've seen with like electronic actuators, they're very expensive. So like by using the syringes, we kind of like cheapen the cost for the consumer.
But as far as learning experiences go, I mean, myself at least, didn't really realize how it would work until we actually put it together and it worked. So I think for people that are trying to learn it, it's a pretty cool thing to see it actually happen.
Yeah,
That's
it's
why I was actually wondering if Lego has such modules.
Yeah, I'm not sure.
I think kids
That's
are just like
curious.
starting to get into like STEM stuff early, so like probably in like the future see more of it.
Let's say if you were given mercury, alcohol, and water, which of the fluids do you think would have worked the best for the story?
Weren't you saying ocean?
Yeah, I don't think it would matter too much because they're basically all incompressible fluids. So I think though with a thicker fluid or something that was sticky, more dense, it might get stuck or it might build up too much pressure and blow the tubes. So I think we would work with water or something that is less dense.
And just use bigger and more syringes instead. Akash wanted to use mercury, but we shut that down.
That was just a joke.
And it's probably not smart to have kids around mercury.
Yeah.
and alcohol.
Yeah.
Any other questions? Thank you so much for listening. Thanks for coming.